That was so late. I had some up that I had a couple mistakes in, so those have been corrected. If you have the ones with mistakes, just make sure you're watching what we're doing here. Okay, so we're now on to 14.6 in your textbook. So this is reaction mechanisms. So far, until this point, minus a few things if you've taken 1210, we've simply been looking at overall reactions. So this is an example of an overall reaction. We have NO2 plus CO forms NO plus CO2 all in the gas phase. But in reality, that's not just a single step reaction. A reasonable proposed mechanism is at below 500 Kelvin is that NO2 plus NO2 forms NO3 and NO. And then the NO3 goes on to react with CO to form NO2 and CO2. So this is a two-step reaction mechanism. Okay. It's a shame that we leave out the really cool part of this section of material, which is how we figure out these reaction mechanisms. Reaction mechanisms are always proposed. Okay, they're never fully determined. There's a lot of very complicated things that go into figuring out reaction mechanisms, but they're usually just a proposed mechanism. We can use our rate laws to go back and confirm or deny that mechanism. But one of the things we can do is measure the mass spectra of products and reactants. And what that'll do is give you a mass for the products that are formed, even if it could be for intermediates as well. And then you can match up a predicted mass with a formula. So just so you know, that's kind of the fun part. That's the analytical chemistry part. That's what my specialty is. Not necessarily mass spec, but anyway, I digress. Okay, so each of these steps is what we refer to as an elementary reaction. And this term's going to be important because it's going to clue you in on the fact that we can actually know a rate law for an elementary reaction. So we can predict rate laws for elementary reactions. Okay. Can't do so with an overall reaction unless you have some experimental details. Okay. One of the other important things to note is that in the first step, NO3 is formed, but then it is consumed in the second step. And it doesn't appear in the overall equation, overall reaction. So we refer to NO3 as an intermediate. Okay. Intermediates also can't show up in your rate law expression. Okay, so we're going to see some examples later on where a predicted rate law might show an intermediate in the rate law. But we're a workaround for that because it's not actually a rate law, a valid rate law. Oops. So a two-step reaction like the one we saw on the last slide would have an interesting looking reaction coordinate diagram, a reaction progress diagram. So let's look at a general two-step reaction where we have A plus B forming AB in step 1, and AB plus B forming BAB in step 2, and an overall reaction of A plus 2B yields BAB. So we can fill in our reactants and products. So In the first step, our reactants are A plus B. They form a transition state. I don't know what that transition state is. It's not expressed in our reaction mechanism. Okay? It also forms an intermediate. So if we take a look at our step 1 and step 2, you'll notice that AB is a product formed, and it's used up in the second step. That's an intermediate. So AB goes in the valley between the two peaks in our reaction coordinate diagram. The other sort of thing to keep note of is that this valley represents the reactants for the second step. So really in this valley, it's AB plus B. Okay? So in the valley is going to be any intermediates and the reactants that'll show up in step 2. If there's other products that show in step 1, they may also show up here as well. And then our products are going to be the products of step 2. And again, we don't know what our transition state looks like. It's going to be something sort of halfway between A plus B in the first step, for instance. Okay. The other thing that we do is classify the elementary reactions based on the number of reactants that are used in the reaction. So we have 3 different types of elementary reactions that we see. Unimolecular, where we have one reactant molecule. Bimolecular, so this is the example from the step 1 of the first reaction mechanism we looked at. We have 2 reactant molecules. And then a termolecular reaction where we have 3 reactant molecules, and these are very rare. The probability of getting 3 atoms to collide properly with the right amount of energy is very, very rare. Okay, it's a low probability of happening. These types of reactions don't take place all that readily. One of the places we do see them is with the formation of something like Br2 with a noble gas. Our halogenated compounds, our halogen compounds, molecules. The little star here is representing excess energy. Okay, I'm not going to show you the mechanism for this, but basically what happens is the argon is simply there to take energy from the bromine plus the bromine. Right? So kind of an interesting reaction, but nonetheless, not super important. Yes?
When you see the termolecular reactions about there,
Yeah.
how much reactions, like, order of magnitude?
It's probably less than that. Like this reaction is one of the only that I've really ever, this type of reaction is one of the only that I've ever really seen. Yeah, go ahead.
And then is it possible to keep something in that transition state for a longer than negligible amount of time?
Yeah, so is it possible to keep a transition state around for any amount of time, really?
For something longer than something 0 than
Yeah, so not really is the answer. One of the other types of experiments that you can do to look at intermediates is ultra-fast laser experiments. So we give energy to molecules to help them form products. And we can use spectroscopy to observe the spectra of those products and intermediates. These are challenging experiments because those intermediates probably are only around for nanoseconds, maybe microseconds. So 10 to the minus 9 is nanoseconds, 10 to the minus 9 seconds. 10 to the minus 6 seconds is microseconds. Yes?
I was gonna ask, how do they know that intermediate,
Yeah, how do you know?
sort of thing?
How do we know that they're a thing?
Well, you can't see them, and they're there for so short of a time. Like how?
Some of them are longer lived, but many of them are not. And even when I say longer lived, it's not like minutes or anything like that. For the most part, there might be a few cases where that's an exception. I'm not 100% sure. But in many cases, the chemistry doesn't make sense without an intermediate. And to sort of imagine a reaction taking place where it just goes from reactant to product, boom, boom, without something in between is actually sort of difficult to imagine. Many cases you need to have a lot of motion in terms of the atoms moving, and so that takes a decent amount of time to do. And so there's got to be something in between reactant product.
So basically, intermediates are theories.
Intermediates probably have started out as theories. Experimental work does prove some intermediates, not everything, because some of them are very, very short-lived. Yeah. But that isomerization one, that's an interesting one. I need to look more into how that became a proposed reaction. I actually looked up. So let me see where we are.
What we saw earlier with with the carbon flipping, is there
Mhm.
is there a bond in that transition state where it's like hanging onto it, or does it completely detach?
I would say it is not a true bond. Again, this was for this specific example, I don't know all of the experimental details. But my guess is, based on other things that I've seen, is not a true bond, but more of a close interaction, more like an intermolecular force than a true bond. Yeah, good questions. Anything else? All right. Let's go back to this. Okay, so our goal is to take our elementary reactions, step 1, step 2, step 3, however many, and produce a multi-step mechanism. They need to be consistent with a balanced equation. So one of the things you're going to want to do when you come up with these, you're not coming up with the steps. When you see the steps of the multi-step mechanism, you're going to find an overall mechanism or overall reaction and make sure that it's balanced. And then from that, from the steps, we're going to be able to predict a rate law and then verify that rate law could be possible using an experimentally determined rate law. So again, rate mechanisms, reaction mechanisms are theories. Okay? They're just a proposal, basically. And we use the rate law to either confirm or deny that mechanism. Okay. All right. Okay, so let's just practice here writing rate laws for elementary reactions. Remember, this is key, elementary reactions. So from our elementary reactions, we can predict our rate laws. If we have a unimolecular reaction where our reactant A goes on to form products, the rate law is going to be rate equals the rate constant times the concentration of A. If we have a bimolecular reaction where we have A plus A yields products, our rate is going to be equal to the rate constant K times the concentration of A squared, because we have A and A. All right. If we have a bimolecular reaction with A plus B forming products, our rate is going to be equal to K times the concentration of A times the concentration of B. Take a couple seconds, fill out the rest of these. So for the termolecular reactions, I'll come around. If you have questions about anything, I'll walk around. All right, do you guys feel comfortable with this? Hopefully. For the first one here, rate equals K times A cubed. The second one, rate equals K times A squared times B. And the third one, rate equals K times A times B times C. Cool. Questions on that? Yes?
Is this a different rate equation than the other one we did, where like the exponent is like the rate log, with like the second living order of the reaction?
So this is different because this is based off of an elementary reaction. The other ones were based off of overall reactions, and we had to use some other information in order to get those.
So it just happens to be like similar units, like K.
Yeah, so the units are going to be based on these rate laws. So you'll have moles per liter inside the brackets. And so, oh, you asked for the units on K. Yeah, moles per liter inside the brackets, and then the rate is moles per liter seconds, and you have to work it out. Yeah. For these, it can be, I mean, it's very doable to work all those out. There's actually a nice pattern that it follows. For the others, though, those are the ones where you're going to need to know the units and how they match up with the order. Other questions? Yeah. Other questions? Okay. So let's look at combining elementary reactions. Let's just take a few minutes here and do these sort of things. We've got a reaction with two steps. I want to know the overall reaction, the molecularity of each reaction, of each elementary reaction, the rate law for each elementary reaction, and if there are any intermediates, write those down. So go ahead and work on that for a few minutes. Dan should be here, right? We're done at 2:45, right? The note you got in Carmen said he was coming Wednesday, right? And this is Wednesday? Okay. It would be, he'll just come up Friday. How's this going?
What is molecularity?
That's the unimolecular, bimolecular, termolecular thing. So the number of, basically the number of reactants. 1 uni, 2 bi. Yep. 3 ter. Should be tri.
Are we not doing that 5 things then?
Well, it seems as though there's some confusion about who was coming, according to the emails I'm getting. All right, just so you guys know, I was emailing the person who said he was coming to do the ExamSoft thing, and he said that it was someone else. So, and she had already told me it was him. So it's a little bit of a confusion right now. Maybe he'll email me, and maybe we will at least do this on Friday. I think that there will be time to do that then. So you'll have to bring your iPads again if that's something you're not normally doing. Okay, so I'm going to go ahead and... Are there questions on this before I start writing things? Okay. So I like to cancel out any products that show up in the first step and reactants that show up in the second step. Cancel those out. And then I like to write out what is left. So I have H2. I'm going to leave off all the phases. I'm going to leave off the gases here. So H2 plus 2 ICl forms I2 plus 2 HCl. Let's see. Oh, okay. Well, I still don't know if anyone's coming. So my guess is no one's coming. Molecularity. So this is referring to basically just referring to the number of reactants in each of the steps. So there's 2 reactants in step 1, so it's bimolecular. In step 2, there's 2 reactants also, so it's also bimolecular. The other thing I didn't check was that my reaction was balanced here in the overall reaction. So that's a good thing to check. I have 2 hydrogens, 2 I, 2 Cl. Okay. To write the rate law, because we're working with elementary reactions, for step 1, we simply take the reactants, multiply them. Rate equals K times H2 times ICl. And in step 2, rate equals K times HI times ICL. All right. What's the intermediate? HI. Yep. So thing that shows up, again, intermediate shows up in the products of one reaction and is used up in the reactant side of another reaction. Serves up as product in one step and used in another step. Okay, so I told you that intermediates can't show up in rate laws, and that's true, as well as this product. I think so that the rate law that we wrote for that second step would not be a good rate law for that reaction, but it's just to kind of give you an practice writing those rate laws for each individual step. I just want to do this real quick. So make sure you can follow along with this reaction coordinate diagram. So we have our reactants H2 and 2ICL. At the bottom of that first hill, we're going to have our intermediate HCl and the reactant in the next step. And then finally, we form our products. Okay? Got an example. Next time, I'll leave it at that. Yeah, so I looked up, this is a hydrogen peroxide decomposition reaction. I was Googling and looking up how this reaction happens with an iodide ion. That iodide acts as a catalyst. We're going to talk about that in a little bit. But this proposed mechanism, which we will say is true for this class, is not at all true at all. There's some really, really cool intermediates that were like, I think there was like HOOI minus, like there were some crazy things that were formed. And they used mass spectra to figure this out. So there's a lot of really cool experiments that you can do with this. Unfortunately, you won't get to do any of them currently, so keep in chemistry and then maybe you will, right? That was totally selling it. Yes.
What school was that work on?
That one, that's a good question. The journal looked old, but I don't think it was that old. It wasn't a very highly regarded journal. I still would trust it, but yeah.